Forgot. There we go. Now I'm recording. So when I do sine to the n minus 1, what you first have to do is bring this power out. Let me do it this way. If I had sine cubed x and I wanted to take the derivative, I would do 3 sine squared x times cosine x. That's chain rule, right? First, you take care of the power 3, reduce the power by 1, and then take the derivative of the sine function, which gives you the cosine. That's exactly what I'm about to do, except the power coming out is an n minus 1. And then sine raised to what power? What do you think?
N minus 2.
N minus 2, right? You have to subtract 1 from n minus 1. So I get n minus 2 of x. And then cosine x dx. Stop it. Tell you. Sorry, I might have to kick him out in just a moment. All right, this is equal to, all right, ultraviolet, right? Ultraviolet's the next step. So I have to multiply these two together, right? Those two together. That's going to be negative. Let me do it this way. Sine to the n minus 1 of x times cosine x. So all I did there was just put that negative that was here. I just put it out in front of everything. And now minus, right? Voodoo, integral voodoo. So minus, I'm going to leave a space. All right, voodoo is this. Right, voodoo is that right there. That looks horrible. Can somebody tell me what constant I can pull out of those? There's a constant in here.
N minus 1.
N minus 1 and a negative, right? See that negative there? I can pull them both. So if I pull a negative and an n minus 1 out, then out front, this will turn to a positive, and then n minus 1 like that. And then inside the integral, I have sine to the n minus 2 of x times the cosine of x dx. All right, that's where I am right now. Is that the formula? Is that what the formula says up here?
Would it not be cosine squared x because you have a cosine in each one?
Oh, I forgot the squared. Sorry, thank you. Yes, cosine squared. Thank you for paying attention to that. I had a cosine here and a cosine there. I would have caught that on the next step. Thanks for paying attention, Brad. Is that what we have up here? No, right? That's not what we have. So now I'm going to do something else. I'm going to rewrite this. And look, as you're watching me do this, keep in mind, again, this is not something that you will be tested on, okay? This is just to show you that these formulas, I joke around. I don't know if I can joke around like this anymore. No, I probably shouldn't go there. I'm just not going to go there. I used to joke around like where these formulas came from, right? Like we didn't just find them somewhere. Like we had to come up with these formulas, right? So this is something that someone really probably struggled with for a long time before they figured out the next step, which was to turn this cosine squared x into a 1 minus sine squared x. That's just the Pythagorean. That's just Pythagorean from pre-cal, right? I'm going to take all this to a new page so I can continue. All right, so here's where we are. Now, distribute this through here to here. So now here's what we've got, equals negative sine to the n minus 1 of x cosine x plus n minus 1 integral. And now when I distribute through, I'm going to get sine to the n minus 2 of x, right? That's the first multiplication. And then what about on the second multiplication? What do I get on the second multiplication? It'll be negative, but it's sine to what power?
Is it to the 0?
2n minus 4.
Almost. You're adding the exponents. You add that exponent and that exponent together. What's n minus
Oh,
plus
Sine
So-
to the n.
sine to
It's
the
just
n,
n, yeah.
sine to the n of x. Good, dx like that. That's what we have, right? So why is that useful? Well, do you remember the rabbit out of the hat problem? Right, from last time? Rather-
Yeah, when you make the original integral equal and
Yeah, it appeared. So I'm gonna bring the original integral over, right? This is the original problem I'm working on, right? Sine to the nx dx. I'm trying to figure out what that is. And do y'all see that I actually have it over here again? You see it appeared over there again?
mhm,
So I'm going to, because I'm doing this electronically, I can cheat. I'm gonna copy and paste this right below it. And what I'm gonna do is, instead of looking at this as an integral of two things being subtracted, I'm going to break this up into two separate integrals. So my first integral is just this guy. And then I have minus the other integral, which is sine to the nx dx. And keep in mind that this n minus 1 would have applied to both of them. So I need to have an n minus 1 in front of that second integral. So I just split it into two integrals and carry the n minus 1 in front of both. Any questions there? Now I need to kill off this one over here, get rid of it on the right-hand side, and that way it can appear on the left. So I'm going to have to, since it's being subtracted, I'm going to have to add, how many of them?
n minus one,
Yeah,
yeah, of sine nx dx.
yep. I'm gonna add n minus 1 of those to each side. So I'm adding n minus 1 of these integrals to this side. And then on the right side, of course, it goes away, right? And on the left side, if I have one of these integrals and I add it n minus 1 of them, how many of them will I have?
N.
N of them. So I have n of these integrals that I'm interested in is equal to negative sine to the n minus 1 of x times cosine of x plus n minus 1 of these integrals, which are a little different, right? This is to the n minus 2 instead of just n. And there's one more step. Get rid of this n by dividing n everywhere, right? Divide that by n, divide this by n. And if you do that step, you will get this. Right? Because the left-hand side will just be this. Now I'm using X, they're using U. The reason I used X is so that when we did integration by parts, we could say U and dV instead of having to use different variables. And then here, this right here, right, is that. But we're dividing by n's and there's a negative, right? So that's just that right there. And then, of course, we got this, which is that, and then that, which is that. So there's your formula. Right?
So you can't do anything with that last integral.
No, but like if your power was, let's just say that this was sine to the third power, right? Then do you see that in your new integral, this would just become sine to the first power? And do we know the antiderivative of sine to the first power? Yeah.
Yeah,
It's just cosine. So the thing is, it doesn't matter what this power is, we could keep using this formula to chip away at it until we get down to something over here that we actually can do. That's
okay.
the power. That's the power of the reduction formula, is that you can use it over and over and over until you get down to an integral that you can handle. So there are some problems in the homework where I believe I did assign them out of this section 6.1, where you can try and come up with the reduction formulas. Not a bunch of them. There's only, let's see, just double check your calendar.
I think it was like 30, like those last two, right? It was like 37 and something else.
35 and 37.
Hmm.
Those two problems right there, 35 and 37, are to try and come up with the reduction formulas that they give you the formula, just like I gave you this formula. They give you the formulas. They say, hey, see if you can come up with that formula yourself. So those are like challenge problems. All right, see how you do with them. I will not test you on that, but it could appear as a bonus on a test. Something like verify this reduction formula, show it's true. Okay, I just wanted to show that to you because all those formulas in the book, every single one of them had to be created somehow, right? Someone had to figure these out. All right, do you want to talk about any other integration by parts? Is there an example you want me to go over? Do you want me to pick something from the book? Are we ready to move on? What do y'all think? I realize that a lot of you have been focusing on the test and have probably not done all the homework for 6.1. So you probably aren't quite sure whether I should move on or not, but I've presented to you all the problems that I normally present in a Cal 2 class in terms of integration by parts. I've shown you the variety I normally show. I'm happy to do another problem if you're interested in it, but I'm also happy to move on. So what do y'all think?
I'm cool with moving on.
Move on? Okay. All right. So let's move on then. And if we have time at the end, maybe we'll do another integration by parts problem. By the way, as you might suspect, integration by parts is not going to go away, right? It's now part of our repertoire of things to do, right? So we might be doing another problem, and in that problem have to do integration by parts, right? Just like when we were doing integration by parts, we may have had to have done U substitution, right? So now it's there, it's with us now. So we're going to be focusing now on trigonometric integrals and substitutions. This section is broken up into two separate ideas. There are what are called trig integrals, that are integrals that involve trig functions and trig functions alone, like only trig functions are within the integral. And then we have another thing that we do in this section called trigonometric substitutions, which look completely different than trig integrals. And so right now we're just working on trig integrals. We will not do trigonometric substitutions today. We will start that next class after our test. So next week, all right? Next Tuesday, we will do trigonometric substitutions. So let's talk first about the things that we do know. Right, so we should all be very comfortable with this first one, right? That's not crazy. Antiderivative sine is negative cosine. We also know that the antiderivative cosine is sine. We even went further than that, right? And we talked about if you had a linear expression inside the sine, then you have to scale out, right? The antiderivative sine of ax would be negative 1 over a cosine of ax. Or if you had cosine of ax, you'd have to scale out 1 over a sine ax. We all good with that? The reason I asked for people to put their cameras on was just because it's easy to like nod your head and I know that y'all are good, as opposed to just looking at a bunch of names. I don't know if anyone's responding. So that we've all done, right? So we should all be like comfortable with those. Now, we need a strategy for solving integrals that involve various powers of sine and cosine. That's the first thing we're going to look at here. What if you have an integral that has sines and cosines to different sorts of powers? How do we attack those? How do we go about them? Well, there's an actual strategy, and this strategy that I have here is on one of your formula sheets. Right, so let me see, where is it? I thought I had it open. Let me, I want to show it to you so that you know what I'm talking about. I have to do this two-step verification every single time I go in. Okay, under your files, formula sheets. Where is it? Trig integrals and substitutions. This one right here. I'm gonna go ahead and download it and open it up. So this right here, this first part shows how you integrate things that have powers of sine and cosine. And there's another section on how we integrate things that have powers of tangent and secant. We are going to start our discussion right now in using this, and then we'll move on to the other one. So what I'm getting at here is that you don't have to memorize these strategies because you can use your formula sheet. You just need to know how to use the formula sheet. So I think the best way to actually do this is to just do an example and then start and then use this and then see how this is all going to play out. So my first example here is this one right here. Oh, by the way, you know the reduction formula that I just proved to you? The reduction formula? You can't use that formula on the test. Because if you look at your reference sheets, it's not on your reference sheets, right? It's not there. So if I gave you like sine to the third power here, you have to do something else, all right? I just showed you the reduction formula just to show you how we can actually use integration by parts to come up with like more general formulas. So how do we do this? Let's bring up that reference sheet. What the heck is it? Here we go. I'm going to zoom in on this and copy these steps. Put them in here. All right, so what we're doing right now is we are trying to solve an integral where we have sine raised to the third power, right? And then inside of that, we have some number in front of t. All right, so we look, how do we integrate powers of sine and cosine? First step we do is we say, if the power of cosine is odd, well, we don't even have a cosine here, do we? Right? We don't have cosine?
No.
Okay, so I'm not even going to do that. Second step, if the power of sine is odd, well, is that what we have? Yeah, we have an odd power of sine. So the first step, if we have an odd power of sine, is to do this. It says here, this is weird language. This is the author's language, not mine. Save one sine factor. Okay, what they really mean by that is to split the problem up where you take one of the factors of sine and you rip it to the side. So instead of having sine cubed, I'm going to go sine squared 4t times sine 4t dt, right? So that's what they mean by save one factor of sine. I peel one of those signs away, right? Now, I could follow the rest of the steps, but I really want you to think about this. If we started with an odd power of sine and we peel one sign off, then this power would have to be what?
To second, yeah.
Yeah, but if it was just generally speaking, if we start with an
Even.
odd power of sine, we peel one sign away, the power that's left will be
Even.
Yeah, even, yeah.
right? Even. So if the sign started out to the fifth power, we'd peel one off, we'd be left with the sign to the fourth. If it was sine to the seventh, we'd peel one off, we'd be left with sine to the sixth. The reason why that's important is because the next step says to use the good old Pythagorean identity from pre-cal, that sine squared x equals 1 minus cosine squared x. So anywhere you see a sine squared of something, you can turn it into 1 minus cosine squared. So watch what I do. This equals, what I'm going to do is I'm going to take here what's here, that even power, right? It's an even power of sine, and I'm going to rewrite it as 1 minus cosine squared of 4t, and then I'm going to leave the sine of 4t there, like that. See what I've done? Rewrote sine squared 4t as 1 minus cosine squared 4t. Now, why is this now going to work for us? Who sees it?
Can you?
It says
take
it in the
out-
steps, but
Is it integration by parts?
well, actually, it's not even that bad. It's not even that hard. It's easier than that.
Can you
Well,
take
You
out a
multiply the sine 4t through.
You could do the sine 4t through. That's not wrong, but what I'm asking you is what method can you use to find the antiderivative of this?
U substitution.
U substitution, basic U substitution. Do y'all see what the U would have to be?
It would have to be the sine of t.
Okay, careful. If U is sine, right? If U is sine, then the derivative is cosine, right? But that derivative is trapped inside the parentheses, isn't it? It's trapped, it's being squared. You don't want that, do you? So instead,
or t?
cosine 4t should be your U. What's the derivative of cosine 4t?
Negative sine t. Sine will be negative sine of 4t.
Negative
but,
sine 4t, then
but the
times
negative
4,
we
right?
can move it out,
Well-
so it doesn't matter.
Yeah, so you have the derivative of it there though, don't you? Here's the
Mhm.
derivative of that. In green, the derivative of the green is the yellow. You're off by a constant. But do you see that it's there? You've got a U and you've got a DU in there.
Wait, so it wouldn't be the derivative of negative cosine squared 4t?
No, I would not include the negative. Here's why. Let me rewrite this. This is the same as 1 minus cosine 4t squared. That's really what that first piece is, right?
Oh,
That's-
okay.
That's what this means, right? So if we're gonna that negative is actually outside the squaring. So I would just use the U as the cosine 4t. Does
Oh,
that
okay.
clarify?
Hmm.
Okay. Let's just take a step back before we do any more. If I have sine to an odd power, right, then I know that if I peel one sign off, right, I peel one off, right, then this power will be even. If that power is even, I can always use the Pythagorean to get this, right, to get something here. And that Pythagorean will always have a cosine in it, right?
Mm-hmm.
And that cosine, the derivative of cosine will be sine, which will be sitting to the side because I peeled it off. Every single time that should happen. So
Mhm.
that's why this is the technique. If you see sine to an odd power, this is the procedure. You peel off the sine, you use Pythagorean, and then once you have Pythagorean, you go,
Oh.
you be the cosine, then the rest should fall out pretty clean.
And the inverse is probably true with the cosine as well, yeah?
Exactly. If we have a cosine to an odd power, we would peel off a cosine, use Pythagorean to turn the other thing into sine, and then go through the method. That's exactly the X that I crossed out here. That's exactly what it is. But let's continue the problem. All right, let's continue. So at this point, I make a U substitution, basic U sub, no integration by parts. U is cosine of 4t. And it says it in the steps right here, in case you're following along here. It says, once you've done that, you make the substitution U is cosine of, whatever it is. Basic U sub, take the derivative of that. You get -4 sine 4t dt. I did all the chain rule and everything all at one time, right? Got my negative out there, my 4. So the green is that. The yellow is that. And so I need to get rid of this -4. So I'm going to scale it out by multiplying both sides by -1/4. -1/4 du equals sine 4t dt. Does anyone have a question?
No, not so far.
We're good. If you have a question, you can just unmute. You can also just, use the Zoom to raise your hand, or you can send a chat. I'm trying to keep an eye on everything. I'll do my best here. All right, I'm ready for the new integral. it's gonna be parenthesis 1 minus, now I'm replacing cosine of 4t with u, but that needs to be squared. And then everything in yellow gets replaced with negative 1/4 du. That negative 1/4, I'm gonna pull out of the integral. And that, I should just be able to use power rule. That's just basic antiderivatives right there. What is the antiderivative of 1 with respect to u? Be careful, what's your variable, right? So the antiderivative of 1 would be
U.
u. So I'm going to put 1/4, no more integral sign because I'm taking the antiderivative. So u, and then the antiderivative of u squared is 1/3 u cubed. So minus 1/3 u cubed, and then plus some constant. And then maybe, well, not maybe, now replace u with cosine 4t. So all I did there is replaced my u's with cosine of 4t. And so on this one, because I was cubing it, I put that cubed right there. That's the notation we use when you want to cube a trig function. I also distributed a negative 1/4 through to both of these. That's why I got the positive 112.
And just so to be clear, you couldn't, when you took the antiderivative of u squared, you couldn't pull that 1/3 out.
Not out with this one, because this would have had to have had a 1/3 as well.
Okay, yeah, that's what I assumed. Like, I was like, I don't think it would have equaled it. Yeah, it wouldn't have equaled the same thing. So there
Yeah.
must,
It-
I was,
You wouldn't have had a great, that's not a GCF, right? It would have to appear in both terms for it to come out. What do y'all think?
So when would you use this one? Or I guess this technique and not the other one that we just did in the other example?
it looks like whenever you have an odd power that it can be reduced to a sine squared or a cosine squared, yeah.
Yes, anytime we see sine or cosine to an odd power, this is the method we'll do. Now, the reason I wouldn't do this, I think I was being asked, why wouldn't we use this? Is that what I was being asked?
Yes.
Well, that I was just showing you, where this formula 73 sitting in the back of the reference page is, like, where the hell does it come from? I'm showing you where it comes from. Now, that was just for like a, hey, wow, that's kind of cool. Like, you can use integration by parts to come up with a pretty cool formula. For us, we're not going to use this formula because this formula is 73, right? There's like 160 or so formulas in the back of the book, right? I let you use 30 of them, but realistically, like, you need to be able to do these by hand, not go reference something. So we're now moving past that, and we're saying, okay, if we see this, what do we do? We see this, what do we do? All right, does that answer your question?
Yes.
Okay.
So, but to add to that question, so you can't do something like this. Actually, oh, okay, I guess there wouldn't be a point in even considering this if you had, say, sine to the first power or something. Like, there would be no point.
Yeah, if you had sine to the first power, you're there already, right?
Mhm.
You have the answer. Like, you should, you know what the answer
Yeah.
to that is. Yeah. All right, let's look at our next example. All right, so following this, I look at this integral, I see sines and cosines, don't I? Sines and cosines. The sine is raised to the second power, the cosine is being raised to the fifth power. Whenever I see sines and cosines, the first thing I do is look to see if the power of the cosine is odd. Is it?
Yep.
Yes, cosine is odd. So I'm going to save one factor of the cosine, which means I'm going to peel one of those cosines off. Here I go. if the cosine started out as being odd, then when I peel it off, I should be left with an even power of cosine, which you can see there, right? Cosine to the fourth now. And the whole point here is to understand that this now is going to be like your du. That's the derivative of something for basic u substitution. That would mean that u would have to be what?
Sine X.
Sine, right? So I need to somehow now get rid of this cosine and turn it into sines. That's where the Pythagorean identity comes in though, right? The Pythagorean identity allows me to switch back between sines and cosines. So let me write the Pythagorean identity up here. This is the Pythagorean identity, right? And you can solve that for cosine or for sine. So if I solve it for cosine, get 1 minus sine squared x, right? My question to you first is, does this formula work for any even? Like, can you do 4 here, and it's still 1? Is that right?
Yeah, because it's 1 to the fourth, isn't it?
Well, I'm asking you all, do y'all think that that's still true? Like, can I replace that with 6, 6, and it's still 1? Like, is the Pythagorean identity only work with squares, or does it work with all evens?
I would think it would work with all
With
even.
all squared? Okay. It's only squares. And here's why. You have to go back to where that formula came from. The formula came from the idea of the unit circle, and that if you give me an angle, theta, the x coordinate is cosine and the y coordinate is sine. And if it's the unit circle, the radius is 1, then the Pythagorean says that this squared plus this squared is 1, right? Pythagorean is always squared. So cosine, this is cosine theta, this is sine theta. Then when you square cosine, right? Cosine squared theta plus sine squared theta must be 1. Pythagorean does not work when you have to the fourth power. That's not what the Pythagorean says, right? A squared plus b squared is c squared, right? So it has to be squared,
Oh, okay.
okay? Which is, I mean, it's not a deal breaker for us. I just don't want people to misuse this. What I've seen people do in the past, they'll take this and they'll say, oh, well, that's just 1 minus sine to the fourth x. And that's wrong. That's
So
wrong.
it's, but it would be like 2 terms of 1 minus sine
Yes.
squared x. Okay.
Yes. Okay, so I'm going to continue now. I'm going to continue and watch what I do. I'm going to do this. Integral. Okay, the sine squared x, I'm actually not, I'm actually happy to see sine squared x because I know that the derivative of sine, right? The derivative of sine is cosine. So that's going to be my u substitution. I just need to get this in terms of sine. So I'm going to rewrite this as cosine squared x squared. Isn't that what cosine to the fourth really means? But then that can be turned into sine squared x. And then cosine squared x, I can turn that into 1 minus sine squared x. And then that whole thing squared. So that step right there, I'm using the Pythagorean identity. I'm rewriting cosine squared x as 1 minus sine squared x, but I'm keeping that squared out here, right?
This is gonna sound probably stupid, but like, how did you turn that cosine to the fourth x to, cosine squared x to all of it squared?
Well, isn't that just cosine x to the fourth power, right? That's what that really means. But I could look at that as being cosine x to the second power, because when you take something to a power and then to a power again, you're just multiplying the powers, right? So 2 times 2 would be 4. So that's all I'm doing is I'm realizing that cosine to the fourth x could be rewritten as cosine squared squared. And then I can use the cosine squared Pythagorean identity to switch to this, but I still have a squared out here. Is that all right?
Yes, now.
Okay. At this point, we're ready for a U substitution. Because I see something in its derivative. The thing I see is sine x. The derivative of that is cosine x dx. I have cosine x dx right there, right? And everywhere that I see a sine, I can replace it with a u. So my new integral will be, what's my first term? What's this?
U squared.
U squared, okay, parenthesis, 1 minus u squared again, right? But then all of that squared. And then at the end, du. Right, everywhere I saw a sign, I replaced it with u. So that's u squared. This is 1 minus u squared, but then all of that squared. And then the cosine x dx matched up exactly to du. I didn't have to scale anything. Now that looks pretty bad, but it's actually just a polynomial. So what I can do next is I can take this and let me just square it, right? 1 minus u squared times itself, 1 minus u squared, and then do my little expansion over here and collect like terms, right? That's all algebra. So it becomes 1 minus 2u squared plus u to the 4th du. I'm not showing that foiling. I'm just doing it mentally and then putting it together. Then I can pass that through. U squared minus 2u to the 4th plus u to the 6th du. And I did all of that so I could just now do each one term by term. So we have 1/3, no more integral because I'm taking the antiderivative, 1/3 u cubed minus 2/5 u to the 5th plus 1/7 u to the 7th. That's just power rule on each one, right? And the final answer is I'm going to replace all the u's with sines. So this is sine cubed x minus 2/5 sine to the 5th x plus 1/7 sine to the 7th x plus c.
I had a quick question.
Yep.
So at that part where you have the u squared times the 1 minus u squared squared, say you had like an impossibly high exponent instead of that outside 2. Could you do u substitution again right here and use like, I don't know, a v?
I don't think that'll help in this particular case, because if you like let this right here be v, this right, like dv is not going to be here. You'll have v squared. That'll be an issue. But it may go. I mean, it depends on the problem. It depends on, is this u, if this is u squared, or is it just u, or is it u cubed? Any problem I give you like this should be doable. Like this should be something you can expand and it's not too bad. I'm never going to give you a problem where it's like this to the 8th power. Like it'll only be like squared or cubed, maybe. That's about the most you get.
Okay, not even like a bonus question or anything like that. Could be.
I can't think of a problem that's ever come up like that where it was something obscene that you had to like do the 7th power.
Okay,
Yeah,
okay,
I
thank
wouldn't
you.
do anything like that. All right. All
So
right.
on that last integral there, did you treat that as like you like mentally breaking it up into 3?
Where?
The very, or the, what, 2
Oh, right
lines?
here?
Yeah, right there.
I just did each one because there's subtraction and addition
Mhm.
between these. I can do them term by term. This one,
Okay,
This one, this one. I can't do it here, right? I can't do it up here because I have a product right there. That's multiplication. So I can't do them separately there. But once I distribute this through, then I have 3 terms and I can do them one by one.
okay, yeah, I see.
Do you think you can explain how you went from step 1, 2, 3, so from step 3 to step 4?
Well, I'm not sure what step 3 is. Just
The one that starts with u squared minus 2u4, and then it goes into 1/3 u
oh,
cubed.
I'm doing the actual power rule, right? I'm actually taking the antiderivative now, right? I want
Oh,
the
you're
antiderivative.
integrating. Okay,
So I'm
you're
integrating,
integrating.
and I'm using the power rule saying, okay, n is 2, so I add 1 to that, I get 3, right? And then I have to scale out front by 1/3. And I'm just doing that for each one of these.
I
That
have a
answers-
question.
Yeah.
Why, so I know we found, or we didn't find it, but we saw that we can make a use of for that sign. How come we
Yes.
didn't do that early on instead of waiting towards the end? Is it because we had to change the cosine to the 1 minus sine squared?
Exactly, because look, if we peel off this cosine, we realize that's gonna be our du, which means that, like, if this is our du, then that means u had to be sine. That means everything here should be, well, if we're gonna have any hope of getting this, the things over here should have signs in them, so I can replace them with u's. See, if you don't do that, what are you gonna replace cosine with? Right? Like, what do you replace cosine x with?
And is that square sine cosine identity, is that in our reference page?
Is what there?
The squared sine identity.
Yeah, it's right here. It's right here. Like it's in here. They give it to you right here and here. But it's also on like reference page for the trig reference page. It's the Pythagorean identity.
Okay, got you.
So when you do the whole like breaking it down thing, like those first steps.
Uh-huh.
So the thing that like when you peel off one, that's always going to be your du. That's just how it works.
Yes. But you have to be starting with the conditions that we started with, right? Is that you had cosine to an odd power, or you had sine to
Right.
an odd power. Now, what if they're even? That's a different story, right? This is not what we would do if they're even. We're about to do one where it's even, but I'm just saying, like, it's a different procedure. Anything else before we move on?
So in reference page 2, fundamental identities is sine squared theta plus cosine squared theta equals 1, and then you just solve for cosine and sine.
Yep. That's where those two equations come from.
Oh, perfect, perfect. Okay, I'll just write it down next to it.
Yeah. Okay, before I do the next example, I want to point out two formulas that are from pre-cal. These two formulas from pre-cal. These are called the half angle or the power reducing formulas. You may recognize these more like this, because in pre-cal and textbooks, they would write them like this instead. Or they would do this. Most pre-cal textbooks, when they present that formula, instead of writing that, they write this. And instead of writing this, they write that. So maybe the stuff in yellow here looks more familiar to you. These are identities that I'm going to need here in a moment. So let's just see how this identity works. It says if you ever have sine squared x, right, sine squared x, yes, of course you could replace that with 1 minus cosine squared x, right? That's sloppy, hold on. Cosine squared x. Like, we know that that's true, right? That's the Pythagorean, yeah. We're like, great, yeah, we could do that. But that's not the only thing you can replace sine squared with. You can also replace sine squared x with 1 minus cosine 2x over 2. And if you pull the 2 out as a fraction 1/2, you get this expression. So what happened here is that the argument of the function x, you can turn it into this, but your argument doubles. These are on your formula sheets as well. Let me see if I can show you where they are.
They're on there. I think they're on the second page, but it's written as the other way you wrote it.
Yeah, let me reference page 2. There we go. Right here. Half angle formulas, right there. Now, when I learned these, the textbook that I learned this out of, I don't know, for some reason, they called these not the half angle formulas. They called these the power reducing formulas. Which to me seems like a better name. Because what happens is you start with sine squared and you reduce that power, you get rid of the squared, and now you have a new expression. Now, yes, I will admit it has cosine in it now, right? But you've somehow gotten rid of the power on the sine and got this new expression. And then here, again, cosine squared, and then you somehow do something and it's going to reduce the power. So I'm just telling you this because you might be in another class like differential equations. They're like, hey, we're going to do the power reducing formula. They're talking about this formula, all right?
Thank you so much.
Yeah. All right, let me get now back to what we were trying to do here. All right, we're going to do another example now. All right. This problem here seems so unassuming. It's just like, oh, cosine to the fourth, beta t, right? Beta, that's just some, beta is just some number. We don't know what it is. It's a constant. We're just going to keep track of it. All right, so let's go through the procedure. Well, it's definitely an integral that has sine or cosine in it. Do I have cosine to an odd power?
No,
No, okay, boom, can't do that. Is it sine to an odd power?
no.
No, can't do that. Oops, I crossed out too much. All right, third thing. If the powers of both sine and cosine are even. Well, here I don't have a sine, do I?
No.
Now you could argue with me that there is a sine to the zero, couldn't you?
Yeah.
Which would be an even power, but I don't have a sine, I have a cosine to the even. So I'm going to do this third step. Okay, I'm going to use this. So what does it say we do? Well, if we have even power of sine or cosine, what we're going to do is use the half angle identities. I'm just going to use these. It doesn't tell me peel anything off, right? It doesn't say peel anything off. It just says use the identities. So check this out. I'm going to rewrite this as cosine squared beta t, all of that, squared dt. Right? I mean, that's what cosine to the fourth means. Cosine squared squared.
Mhm.
Oh, I erased the
Oh,
square.
yeah.
Put it back. There we go. Cosine squared squared. Ethan, we good with that? You got that? Okay. All right. And then next, see, I'm not going to use Pythagorean, right? I'm not using Pythagorean because when it's even, it tells us, doesn't tell us to use Pythagorean, right? It tells us to use the half angle identity or the power reducing. So I'm going to use this one right here because I have a cosine squared in here, don't I? Right there.
Mhm.
I'm going to use that formula and watch what this becomes. Parenthesis. Okay. The formula says I'm going to have a 1/2. Okay, 1/2. Then parenthesis, 1 plus, and then cosine of twice, right? Look at the formula here. Double whatever the angle was, right? I'm going to double whatever the argument was. So I've got a double beta t. So I'm going to have here 2 beta t. Close that. The whole thing squared dt. That's just me turning this green piece into this green piece.
There should be one more parenthesis on the left side, I think, or no?
I think I have all parentheses in place. Right, I've got.
Oh, yeah, I see it.
1, 2, yeah, I've got 1, 2, 3, 1, 2, 3 opening and then 3 closing right there. All right, we good?
Yeah, so far.
Now, what I'm gonna do is I need to square this. I'm actually gonna square this. So see that multiplication? I've got a multiplication right there. I'm going, because when you have multiplication, like if you have X times Y and you square it, you can square the X and square the Y. You can do that with multiplication. I'm going to square the half. And then I'm going to square this whole thing. So just let me write it down, then we can talk about it. So I'm gonna have a 1/4. That's what happens when I square 1/2. Then I'm gonna have 1 plus cosine of 2 beta t. That whole thing needs to be squared and then dt. I'm gonna pull the 1/4 out of the integral. And then I have to square this, right? I still have to square this thing. Which means I'm gonna multiply it times itself. That's what squaring that means, right? If I'm gonna take this parenthesis right here and square it, I've got to multiply that times itself. No, still good?
So
Let's
this
go.
is like a faster way of doing it.
This is it. You're seeing it. Yeah, this is brutal. This problem is brutal. Let's just keep going. Well, the fastest way is just go to Wolfram Alpha or something. Simple.
Well, yeah, no, but that's no fun.
It's like he
Yeah.
knows.
So here, right? I'm gonna do that now. Foil it out, expand it. 1/4 integral. All right. So 1 times 1 is 1. That's my first multiplication. Let me go through a little slower here. So that was 1 times 1. And then now I do 1 times cosine of 2 beta t, which is cosine of 2 beta t. And then when I do the inner one, I get the exact same thing. So plus cosine of 2 beta t. And then the last one, this is the one that sucks, is going to be cosine times cosine is cosine squared. So I have cosine squared of 2 beta t dt.
So do you use the identity now for the cosine squared or no?
I'm gonna have to use the identity again on that cosine squared, but let me get to it. Let me clean this up first. 1 plus, this is 2 cosine of 2 beta t. So all I did there was combine these two together because they're like terms, right? They're the same exact thing. I have 2 of them, I add them up, I get 2 of them, right?
Mhm.
And then I still have plus cosine squared of 2 beta t dt. Now look at these integrals. They're all separated by, or sorry, take a look at this integral. I have separation addition here, right? So I can do them one at a time. Let's put a 1/4 out here and let's put a bracket. All right, what is the antiderivative of 1 in this particular case?
BT.
Just t,
Oh,
right?
that's right, yeah.
Antiderivative of 1 is t because we're integrating with respect to t, not x or u or anything else.
So I have a question before you go
Yep.
any further.
Yep.
Could you be able to pull out a constant since you have a 2 in front of the cosine?
Well, the 2 would have to be in front of all of these. If we want to pull a 2 out here, we'd need a 2 in each one of these,
You're right. Okay.
which is why I put a 1/4 and then put a bracket.
Got you. Okay.
And I'm just gonna do each one of these. All right, plus this 2 is gonna come for the ride, and now you get the pleasure of giving me the antiderivative of cosine of something.
So sine 2 BT. Oh, actually, no.
Sine
It would
2
be,
beta t, but remember,
you
you're
need the
doing the
1/2.
antiderivative, so you have to scale, don't you? That was
yeah,
like when we first started this whole thing,
1/2 beta.
1
Yeah.
over 2 beta. Good. 1/2 beta sine of 2 beta t.
so
Very
beta is a constant here.
Beta is a constant. We're treating beta
Gotcha.
like a number. We just don't know what it is. All right, everyone see that? 2 just comes. And then we actually found the antiderivative of cosine of a linear expression the antiderivative of cosine of a linear expression would be 1 over the a, right? The number, the coefficient in front of the variable. For us, that's 1 over 2 beta, and then sine of 2 beta t. Okay, is that good so far? Is everyone okay with that?
Mhm.
But I still have plus, and now I need the antiderivative of this, don't I?
Yeah,
I don't know what that is right offhand. I can't just do that mentally because it's squared, right? It's a squared. It's not just cosine. So I'm just going to put here the integral because I don't know what it is yet. And I'm going to close my bracket. All right, let me write the next line. 1/4 t. And then on this one, the 2 and the 2 cancel. And I'm also distributing. So I'm distributing here. I've distributed 1/4 through. So I have plus 1 over 4 beta. Right, the 2's went away. So I just had 1 over beta, but then I multiplied times 1/4. So I get 1 over 4 beta. Sine of 2 beta t. And then I also have to do the 1/4 to this integral. So I'll keep this in blue, plus 1/4 integral. And then this piece, this right here, I need to take the antiderivative of. So we are back to the very beginning of the problem where we say, hey, what happens if you have cosine to an odd, cosine to an odd, sine or cosine to an even? This is the case we have, right? We have cosine to an even again.
mhm.
So I've got to use that formula again. So this is going to become, according to the formula, 1/2. I'm using this right here. I'm using that right there. So I'm changing it to 1/2, 1 plus cosine of, really important, this step, double the angle, right? We want to double whatever the argument was,
Oh, so 4bt this time, right?
or beta t. We're doubling 2 beta t, so it becomes 4 beta t. If that was a 3 beta t, it would now become 6 beta t. If it was a 10 beta t, it would become 20 beta t, right? You're doubling whatever the argument is. So 4 beta t dt. And I keep going. 1 over 4t plus 1 over 4 beta sine of 2 beta t plus 1/8. I just brought the 1/2 out with the 1/4 integral of parentheses 1 plus cosine of 4 beta t dt. And I can do each of these separately now because I have an addition sign between them, right?
Mhm.
First time students ever see this problem, they're like, really? Really? It's all this work? Really?
I don't even, I didn't think it was that bad. It's just that there's a lot of places to make a small error.
Oh, yeah. Yeah. You just have to be very meticulous with this. Antiderivative of 1 t.
Yeah.
Right? And then plus now antiderivative of the cosine of 4 beta t. We did one like that earlier, right? We had to scale, we had to do 1 over, this time 4 beta sine of 4 beta t. And then close it off. Plus c. Oh, yeah. Okay, I'm gonna go to my next page. Bring that with me here. I'm gonna clean this up. There's still a little bit more I can do here. Okay, I just distributed the 1/8 through. And the reason I did that is because these two are like terms. I have a 1/4 t and I have a 1/8 t. And 1/4 plus 1/8 should be 3/8.
Yeah,
So we get 3/8 t, this is my final answer, 3/8 t plus 1/4 beta sine of 2 beta t plus 1/32 beta sine of 4 beta t plus some constant. That's the antiderivative of cosine to the 4th of beta t. That took up quite a bit of space, didn't it?
Are we able to combine the 1/4 beta and the 1/32 beta? If we wanted to?
No,
because they
because
have different.
these would have to be the exact same expressions here. And they're not.
Okay,
And right, remember with the way sine and cosine work, you can't just pull out a 2 out of this sign, right? You can't just like factor a 2 out and make them look the same. So this is it. We're stuck. Like this is where we're at.
So, you know, going back to the if you go back to the very beginning of this problem, so were you able to, when you made it, when you broke it into like, I don't know, cosine squared, BT squared. So it says to use the double angle. Now, can you just use the like if you use the Pythagorean identity alone, do you end up in the same place or?
The problem that you run into, right? Let me show you. It's a good question. Right, because maybe there was another way and maybe wouldn't have been that bad. But let's just say we would have started with this. Let's say instead we would have done integral and then use Pythagorean, right? 1 minus sine squared beta t, right? Something like that, and then square dt. Well, then let's square that, right? So if you square that, I'm not going to show the work, but it would be 1 minus 2 sine squared beta t. We'd have 2 of those, and then we have plus sine to the 4th of beta t, and then all of that dt. And the problem with this is that what you're missing out here is that cosine t that you would need to do a u substitution, right? It'd be great here, we just let u be sine, but see, you don't have a cosine.
Yeah, that's true.
So now what you've done is you took, right? Remember the original problem was cosine to the 4th beta t. And what you've done is you created something that now has a sine to the 4th beta t and a bunch of other stuff.
And
So
so,
it's
as
more
we're-
complicated now.
yeah, I was like, and so you can't break that up into 2 different integrals and then make that 1 minus 2 sine squared into like a, what, like a 2 cosine squared?
Yeah, well, if you're, well, yes, I mean, there's a bunch of other things you could do, right? But if you stick with Pythagorean, you're not going to get anywhere.
Okay,
At some point, you're going to need the half angle, or what I'm calling the power reducing. At some point, you're going to need that in order to get this to go.
okay, yeah, you're probably just gonna infinitely loop or something.
Yeah, it'll probably just get worse and worse, or you eventually do it enough times, you wind up back where you started. You're like, oh yeah, this all turns out to be cosine of the 4th beta t, and then you know. Now look, I want to show y'all. I'm gonna go to Wolfram Alpha, and I'm gonna ask the Wolfram to do this for me. So let's see. I'm gonna do cosine, and I'm just gonna put b times t. And then I'm going to integrate this with respect to t, and let's see what we get. Oh, wait, I forgot the 4th power. Duh. Hold on. I need all this to the 4th power. So let me take all of that to the 4th. And there's their answer right there. Which is our answer, right? If you notice you have one denominator, split this up into 3 different pieces, 12 beta t over 32 beta. 12 over 32 would reduce to be, what, 4 goes into 3/8, and then the b's cancel, you get 3/8 t, and then
Mhm.
Here, this over that, the 8 and the 32, you get 1/4 beta, then sine 2 beta t. This is right. I mean, it's correct. Wolfram did a little bit faster though. Now, when I'm giving tests, this doesn't happen a lot with my face-to-face classes, but I also do a Cal 2 that's online. And when students turn in like work and they give me this answer, I know they didn't do it, right? Because this is the computer's answer. A human's never going to get to this. Like, you're never going to get this answer, right? You're never going to get the answer we just got.
That kind of looks
Oh, let me get
calculus
a common denominator now, put them together. Like, you're never going to do that, right? I mean, you're just not.
Yeah,
So it's so easy in an online class in calculus to see when students are using technology and just getting to the answer that way. I'm letting you know that because it's obvious to anyone who has any experience with calculus when a computer is being implemented and when it's not. It's very easy to see.
that's what I assumed as well, honestly, when
Yeah.
it comes to that.
Especially trig stuff, because trig stuff also involves identities, and the computer will use identities that a human would never use. And then the answer looks way different. Maybe even as simple as like, let me do, what did we do? The first problem we did was, what was it? Cosine. Hold on. First problem we did was sine cube 4t. Let's just see what it does. So I'm going to say sine cubed 4t. We'll just leave it as t. Oh, perfect example. Perfect example. Look at the computer's answer. Right? Is
Yeah, I
that
don't
what we
even,
had?
I
Not
don't-
even close,
yeah, it
right?
doesn't even
Not
look
even
like it.
close. Because what the computer did, if I go back to my answer, where was mine? Yeah, this is it, right? Right, this was ours. What the computer did is they took this cosine cubed, they probably peeled off a cosine squared, then they used the half angle or power reducing formula, and then started to, I mean, the computer is going to do all of that in an instant. Like, it's no problem for the computer to do that. So this is the way a human would do it. There's no human being that is going to take that answer and get me to here without another 3 pages of work. You know what I'm saying? So I say this in the way that, like, I'm teaching a Cal 3 right now, and they have a midterm and a final, and then they have 8 take-home exams, right? They're smaller exams. There's like, 3 problems, 4 problems, right? But I tell them you can't use a computer to solve certain things. And when I see this, do you see how obvious that is? See how obvious this is? So then I ask a student to defend your work, right? How do you defend that, right? So I'm just telling you to be careful, not necessarily if you're going to be in Cal 3 with me, but just any other class that you're in where you're not supposed to be using technology, and then you go use it and turn it in. Just know that you can get caught very easily. And then if the professor is a real, hard ass, you might be in front of some panel trying to defend your academic integrity. And, that can go on your record. And I mean, it just depends on the professor. And I've been on committees like that, and it's impossible for a student to defend this. I mean, they can sit there and say, oh, I did it. And then we ask, how did you do it? Show us. And I just do it in my head. Oh, really? Really? You do it in your head? Okay. And I've seen people that they just will not admit it, so just be careful. That's all I'm saying. Technology is great. It's a great check. It's a great thing, a tool for us to use. But in academia, if you're told not to use it, you got to be careful. It's easy to get caught. All right. I hope that convinces you a little bit. All right. What else we got? We got 20 minutes. Let's see where we are. What about if we change it up and now we do integrals that involve secant or tangent? So in this section, we can handle sine, cosine stuff. And we can handle tangent secant stuff. All right. If you mix me up some sines and like tangents, I may not be able to get it. It just, this is a very limited thing we can do. But there's a technique if we see a certain pattern within our integrals. Maybe I should put it this way. If you were to take a bag or a bucket or whatever, and inside of this, you had all functions you could ever think of, any function that you could ever come up with, anything, put them all into this big old bag or bucket, right? If you were to reach in here, close your eyes, reach in here and grab one out of here, right? Pull it out, there it is, boom, there's the f of x, I just pulled out, there's some function. If I ask you to take the antiderivative of that, the probability that you can find the antiderivative of that is essentially 0. What I'm saying is that, like, we in Cal 2, we are very careful about what we present to you to find the antiderivative of, because like in the real world, like the chance that you're going to be able to find the antiderivative using these techniques is essentially 0. Because there's so many functions we can't find the antiderivatives of. Isaac, I see your hand up, hold on. We can't do them using our techniques. Now, when we get to chapter 8 and we learn about series, then that's the workaround. Like there's a workaround to this. So I can't do this in general, but if you let me do it with series, I can do it. Okay. Which is why series are so important. All right. All right. So Isaac, was there a question?
Yes. How'd you feel when you were talking about Wolfram Alpha? I remember in 2013 using my math lab a lot to help like solve my problems and learn how to do it because they gave examples like a human would to solve their problems. How do you feel about like those?
I don't really see a problem using the technology to help you learn, right? To help you learn. And show you like the human steps is like, hey, make this substitution, blah, blah, blah. I think that's good if you're using it as a tool to learn. But when it comes to something where you're being assessed on what you know, then you need to be able to do those things, right?
Yeah, true.
So
That's
it's a good
of
tool.
course.
It's a good tool, but it's not, it doesn't replace you, right? There are problems that, you know, we're still at a point right now where computers can't do things that we can do, right? Like take a real world problem and convert it into the math, right? Like we're not at a point yet where the computer can do that. We still need to like do some translation for the computer. Although it's getting crazy good, right? Have y'all heard of that? What is that thing called? The chat something?
GDP.
Yeah, have y'all heard of that?
I refuse to use that thing. That thing scares me.
That
I mean, right
Yeah.
now, the fact that you can go to like Wolfram Alpha, put in an integral, and that it can show you a step-by-step solution, like that is nuts, man. Like that is crazy because it's abstract. You can do pretty much it's symbolic, right? So for years and years, computers have been able to like find integrals as long as, well, we haven't talked about it yet, but if you're trying to find area under a curve, it could do it because it's just numerical. But symbolic manipulations are something else. And so we've come quite a ways, but do we really want to go all the way down this road? Because then
I
what's
don't
the
want
point?
Skynet doing my math for me. No, thank you.
What's the point of you going to school and getting any degree if a computer is going to be better at the job that you're trying to do, right? What's the point, right? And then what's the point of us at all, right? If a computer can do everything we do better.
Me sweating right now as a computer science major, just profusely.
No, it's
So, I mean,
okay
there-
because you'll still have to be hired to make sure that the chat GPT code works.
Well, I will,
well,
but
unless it can edit its own code.
oh
Okay,
yeah, yeah. Well, yeah, exactly. Some people have theorized and questioned that, but that seems
Yeah,
like
this is a rabbit hole. Let's not go down right now.
exactly. It's
I
a
do have
rabbit hole.
one more question. Does Alamo Colleges still use my math lab for their online courses? I'm just curious.
certain ones. Once you get to the calculus sequence, they don't use the MyMathLab.
I see. Okay.
But it also depends on what school you're at, because if you go to a different, if you go to like SAC, you might be using MyMathLab for calculus. If you go to St. Philip's, you might be using something else. It just depends.
I just preferred it a lot, actually.
Okay. All right, well, let's in the last 15 minutes here, let's at least get warmed up with where we're headed with this tangent secant thing. So remember in the beginning of this, I said before we even started with the sines and cosines, we had to remember like basic stuff, antiderivative sine, antiderivative cosine, and then if there's a linear in there, we have to scale, right? Those are like the basic things you need to know to do sine and cosine. Well, if we're going to do integrals that involve secant and tangent, there are some things that we need to know. So we already know that the antiderivative of secant squared, right? The antiderivative of secant squared is tangent. Like that we know from Cal 1, derivative of tangent secant squared. And then we also know that the antiderivative of secant tangent is secant, both, right? Because the derivative of secant is secant tangent.
Yes.
Those are like the main things. And then of course we could put linear expressions inside of those, which would require us to then scale 1 over a, 1 over a. That's the beginning of this. And then what we do is we get these steps again, just like we had, and those actually appear on that same page I just showed you, right? This right here. Actually, I need to bring up the whole thing again. Did I close it? I downloaded it. Let me get it. So this right here, it's over here on the side. These are the new steps for tangent and secant. I'm gonna just slap them in here. And let's try, we've got enough time. Let's do one of these. Oh my goodness, come on. All right. So here's an integral that involves tangent and secant. And let's just follow through with this procedure. All right, if the power of secant is even, that's what we have here, right? We have an
Yeah.
even power on secant. Then what we're going to do is we're going to peel off not one secant, but 2 of them. We're going to peel off a secant squared. That's what this next thing says. Let me do that. If I peel off a secant squared, then that should leave me with a secant squared as well, right? Because it was secant to the 4th.
Oh, yes.
And now, again, using that same kind of thinking, this thing I peeled off is going to be my du. That's the derivative of something. What is it the derivative of? What do you take the derivative of to get secant
Tangent?
squared?
Yes.
Tangent, right? Tangent. So that means you would really like it if the rest of your expression over here had tangents in it. And
Okay.
part of it does, part of it doesn't, right? But we have this Pythagorean identity, right? There, remember in pre-cal, there was 3 different Pythagorean identities that were all related to one another, but this is one that hopefully got beat into your head a little bit in pre-cal. I realize it's been a while, but that's an important Pythagorean identity. These are on your sheets. And so what I'm going to do is I'm going to replace secant squared with 1 plus tangent squared. And I'll still have that tangent to the 4th out there.
Okay, so it'll put the whole thing in terms of tangent.
Yeah, except the secant squared x dx, which is going to be my du when I do a basic u substitution.
Mhm.
Any questions on that? All right, u is equal to tangent. It says it here, in case you don't want to have to think too much about it, it says what to do. But I'm doing it more of like, hey, I know that this is the derivative of something, therefore the something needs to be tangent. And now I just rewrite everything. So I've got u to the fourth, 1 plus u squared. And then secant squared is just du. So it's actually pretty clean if you look at it now. Distribute, so I get a nice clean polynomial. Add exponents, right? And now power rule. 1/5 u to the 5th, 1/7 u to the 7th plus c. And then replace your u with tangent. So tangent to the 5th x plus 1/7 tangent to the 7th x plus c. There you go.
Is there a similar method to this with cosecant and cotangent or no?
Yeah, there is, but the thing that you would have to know there is like, what's the derivative of cotangent? What's the derivative of cosecant? And it would work the exact same way. It's just most textbooks don't go down that road. They usually just do sine and cosine, and they do tangent and secant. And the reason they do just those two is because, like, if you can do secant and tangent, then everything can be rewritten. Like if you have something with cotangent and cosecant, you can always rewrite those in terms of tangent and secant, which if you have tangent and secant, you can rewrite those in terms of sine and cosine. Like, we don't need all of them. Let me try and rephrase what I'm saying. We could have, in the very beginning of this problem, we could have, if we wanted to, and this is something that actually I was going to say right after we finish this problem, is to keep in mind that if you ever get stuck on a problem, you can always turn it into its same form, but in terms of cosine and sine, right? Like that's the same. And then you could try and mess with this. This would be like really tough to do, but I'm just telling you, if you're doing a problem for homework and you get hung up and it has tangents and secants or something in it, just try and write it in terms of sine and cosine and see what happens. Maybe it'll go easier that way.
Would it be possible to go back and instead of using this method, combine the tangents all together, leave the secant squared x separate, and then do integration by parts instead?
Maybe you could do that. You mean like distribute this through?
Right.
And then do integration by parts on what's there? It might go.
Okay.
It might go, but I think that would be a lot,
Be a lot more
harder.
work. Okay.
Yeah. Yeah, I don't think that it would go easily with integration by
Okay.
parts, and it may not go at all.
Okay.
Right? Because remember, the integration by parts is not like the magic pill that solves all integrals, right? Like it's very useful in certain scenarios, but not in every scenario.
Okay.
I have a quick question. Going back to if you're going to distribute that tan, could you have done that, and would you have still gotten the same answer?
Yeah, because if you distributed that, you would have had tangent to the 4th x plus tangent to the 6th x, and then you would have had secant squared x dx. And then when you did the substitution, you would be directly at this line right now, right here. Like you would just have u to the 4th plus u to the 6th du right there.
Okay, so it's just really for preference.
Yeah. I think when I was a student, I always distributed this out first, but then later when I started teaching it, I said, there's no need to distribute it at this point. You just leave it as long as you've got nothing but tangents there and then a secant squared off to the side, may as well just make your substitution right now.
Okay, got you.
Yeah. Curious to see what the computer does with that. It should be a mess. Let's see, it's tangent x to the fourth secant x to the fourth dx. Yeah, here we go again, right? We've got a cosine 2x in there. Like, where in the world is that coming from, right? Was that the same problem? Oh, yeah, it was secant to the fourth. Yeah. So, yeah, nobody's getting this answer. No humans doing this.
Can you show the step-by-step on it, just out of curiosity?
I don't know if I can. Do I have to pay for it or no? Or not?
I was wondering that too.
Yeah, I gotta go unlock
Okay.
the pro version.
Oh, that's so funny.
Yeah, yeah, they're all like that.
Yeah, I don't know how good that explanation would be, to tell you the truth.
It looks like they did the
I'm
same
willing to
thing
bet
as
somebody
what
in
you
this
did
class
so
is
far.
paying for some service.
I am.
Get them the answer. Are you?
I don't use it very often.
Why pay for a service when you could just buy a graphing calculator?
Well, you need one that can do symbolic manipulation to get
No,
this.
no,
answer.
no, not that, not those. Those are cringe.
Symbolab, all right, so we try Symbolab. Got it. Okay, so let me see here. Yes, I'm aware of Symbolab. Let's see, tangent x fourth secant x fourth. Do I have to put dx here? Probably. Ooh, that's better. Look at that. That's nice. You know what we got? Look at that. Symbolab did better. Show step.
Even a blind mice can find cheese sometimes.
Yeah, no, they did good. So it's, yeah, this explains all the steps. You have to unlock some of the intermediate steps, but it tells you right here what the, well, no, it's locked. Rewrite it using trig identities, apply a U substitution. Doesn't tell you what the U substitution is though, right?
Oh, yeah.
And then expand. If you have to pay to see this step, then you got bigger problems. Right?
So if we pay for the pro version, then we can cheat on these online tests. No, I'm just joking around.
Yeah, exactly. There you go. Now you got it. Well, you have to hope. I actually, I'll stop recording. The worst